In this recording, we're going to discover the remainder theorem, which is a very useful and powerful theorem as it relates to finding zeros of polynomials. As you know, we can factor quadratics. We can also solve them by the quadratic formula. But after that, many higher order polynomials, cubes, quartics, beyond that, it gets really difficult to find the zeros algebraically. So this tool, once we discover it, will be useful to us. So what we're having you do here is, it says use polynomial long division to do this division. You may use also synthetic division if you're comfortable with that. And then it says evaluate P of 2. So I want to walk you through part A, and then have you guys work on the other three parts. So first off, I'm going to use synthetic division just because I find it to be handy. So to divide this quadratic by x minus 2, if you remember, we write 2 because it's x minus 2 is the divisor, so I just changed that minus 2 to be a positive. Then I write out the coefficients of x squared, so it'll be 1, negative 8, and 18. And then it's pretty simple. It's bring down the 1, multiply 2 times 1, 2, add, negative 8 plus 2 is negative 6, multiply 2 times negative 6. Something got funky there. Let's clean that up. And then add. Okay, so this says there is a remainder of 6. Okay, so in terms of expressing this, I would say we have x minus 6 plus 6 over x minus 2. That's what that extra 6 is on the end. Now let's work out the right-hand side. So it says evaluate P of 2. So P of 2, just sub in the 2. And do the math either on your calculator or in your head. I'd like to try to do it in your head if you can. So that's 4 minus 16 plus 18. Well, 18 minus 16 is 2. 4 plus 2, 6. So P of 2 is 6. Okay? Let me have you do parts B, C, and D, and then play the recording when you're ready to go over how you did. Okay, so I'll kind of work these out quickly, and then we'll try to reach a discover a conclusion. Okay. So it means we've got an x plus a 5 plus a remainder of 10, which we'll divide by x minus 7. All right, and work out P of 7. And that, in fact, works out to be a 10. Hopefully you're noticing a pattern here. Let's work out the third example. Okay, and finally, and if you haven't been working these out on your own, you've just been writing down what I have, please work this out on your own. You need the experience of doing so. Let's hopefully work this last one out as well. Okay, interesting. We have a 0 as the remainder here, so I can write it just as 3x minus 5. I forgot to write the previous one out. Let me do that. This would be a 2x plus 5 with a remainder of negative 4. So I'll write negative 4 over x plus 3. Okay, and finally, new color. When you work all that out, it works out to be 0. Okay, so hopefully you recognize something. Hopefully you recognize that that number that's our remainder is the same exact value as the value of the function when we evaluate it at that particular value of x, which is pretty powerful. So what it's saying is, if we have a 0 as the remainder, that means it divides in evenly. That means the function is going to produce a 0. It's going to produce a 0 at that particular x value. And that kind of makes sense. This is a factor when this opposite number, negative 4, is a root, right? So let's take a moment to take this in. Okay, so just kind of summarizing what we saw, if you have a polynomial that you divide by a factor like x minus a binomial, the remainder will be the same as when you evaluate that polynomial at that value a. So remember, like when we set up our synthetic division, we always take a and put that to the side. That's the number that represents this factor in the synthetic division. So let's have you spend a little time working out exercise 2. Play the recording when you're ready. Okay, so hopefully you took the time to work this one out on your own. So we're going to divide this. I'm going to change the x minus 9 to a 9. That represents the divisor x minus 9. I'm going to write out 1, negative 11, 22 for the coefficients of the dividend, the thing we're doing the division into. And then we just do our synthetic division. So bring down, multiply, add, multiply, add. So the remainder is 4. And so 4 is the value of r. Okay. All right, example 3, or exercise 3, it says, these days, the remainder theorem is primarily used as a justification for telling if a linear expression is a factor of a polynomial. So what we're saying here is, if x minus a is a factor, that means when we divide out the polynomial by this factor, there's just a quotient. So there's no remainder, what it's saying. So what must be true about the remainder if it is a factor? Well, the remainder, okay, because x minus a divides in evenly. Okay. And finally, we're going to determine if each of these are factors by evaluating the polynomials. So if I want to know if x minus 3 is a factor, I'm going to work out p of 3. Because if it comes out 0, then I know x minus 3 is a factor. So let's just do 3 squared minus 11 times 3 plus 24. And yes, in fact, 9 minus 33 plus 24, it is 0. So I would say yes, it is a factor. Okay? Can you work out b, c, and d? It's funny how d and c are switched there, but I'm sure you can handle that. All right, so if you haven't done so yet, please take the time to work this out. But I'll work this through for you if you have. So we're going to first turn this into a root, so negative 5, and we're going to evaluate p of negative 5. It turns out when you do the math there, it comes out to be 3. And again, we said in order for x plus 5 to divide in evenly, it would only divide in evenly if this remainder were a 0, so we're going to say no. Now you might look and say, hey, look, 5 is never going to divide into 2 anyway, and you'd be right. Whereas 3 is going to divide into 24. Okay, finally. This one has the potential, so 1 could divide into negative 3. Let's see if in fact it does. So we're going to change this to p of negative 1 and do the math. When we work this one out, it does come out evenly, so we'd say yes. And finally, you might say, does 5 go into negative 10? Well, negative 5 go into negative 10? It could. So, again, we'll work this one out. So we'll go p of 5 and evaluate p of 5. When you evaluate that, it works out to be negative 5. So no, it does not. Finally, for what value of k will x minus 4 be a factor? Show how you arrived at your answer. Hopefully you thought about this one and tried your best to work it out. Let me get you started on it. Let me get you thinking about synthetic division. So if I have a 4 here, and I lay out my 1k negative 52, do what you can with this. Why don't you work out your synthetic division here and see how far you can get. Okay, so we'll bring down a 1, multiply 4 times 1. add k and 4, I get a k plus 4. Now I'm going to multiply. I get 4k plus 16. I'm going to add those, and I get 4k minus 36. Okay, now think about it. What did I need for this to be in order to have it be a factor? Right? I needed this to divide in evenly. I needed this to be a 0. So we're going to find out what value of k would produce that. And that's just some simple algebra. So 4k equals 36. K would have had to have been 9. Okay? So if k is 9, then I can divide evenly 4 into this polynomial. Thanks for watching.